Okay, so the new force, like I said, normal force. And in physics, normal means what? What is that symbol indicating? If something is teed up to something else. Perpendicular, right? Okay, so in physics, if something is normal to something else, that means that it is perpendicular to it. Okay, so for an object at rest, mg is acting downward and is often balanced by normal force. Okay, so this thermos right here. Okay, if we set it down, what's the F net for something sitting on your desk? Yeah, not a trick question. F net 0. Okay, so is gravity acting on this thing? Also not a trick question. Okay, gravity's acting on it, so gravity must be balanced out by something else, and that's normal force pushing back up. Okay, mg down, normal up. They're balanced out, F net 0. Okay, so it's a contact force. It's a force when something is contacting something else. All right, so today we're going to learn how to do an FBD. Okay, and these are very important. So, FBD. Probably one of the most important things in introductory physics is how to do a free body diagram. Okay, and basically a free body diagram, you take the object that you care about in the problem and you draw all the forces on it. You draw all the force vectors. Okay, so we're going to take very easy, boring situations today. Boxes sitting on table. How exciting is that? Didn't you guys ever always want to learn about things sitting on things? Isn't that why you took this class? Okay, it will get more interesting than this, I promise, but we gotta know how to deal with normal force before we go on to things like friction. Okay? Alright, so we got 4 situations. We've got to do an FBD, and we're going to analyze what weight, normal force, and F net are doing. Okay, so we got 10 kilograms just sitting on a table. Determine the weight of the box and the normal force acting on it. Okay, so an FBD always starts with a dot. And all of the forces come out of that dot. We'll start out with mg. Force of gravity is mg. Question? Oh yeah, you guys got to draw them. It's a rough life. Yep. Okay, so there's mg. And that is equal to 98 newtons. Okay, all I did was take 10 times 9.8. Okay, now it's just sitting there. We already said that F net is 0 newtons. So mg has to be balanced out by another force. Let's say this was the only force there, just mg. What would the thing be doing? Falling, free fall. That's right, it'd be in free fall. Okay, so balancing mg out, I'm going to draw it the same length, is normal force. And we call that F sub n. And it is a capital N. Sometimes we will just write capital N for normal as well. That works too. Yeah, capital N is also Newton. So if N is written after a number, we know that's the unit newtons. If it says N equals, that would be normal force. You'll see both of those. Okay, so this is also 98 newtons. Everything balances. F net is 0. Okay, another situation. Someone is pushing down with 40 newtons on the same 10 kilogram box. Okay, so the thing's sitting there, and then somebody walks up and pushes down on it like that. Alright, so let's draw all the forces. is gravity still acting? Yes, because someone is pushing on it is not going to change the fact that the thing still weighs 98 newtons. So I'm going to say force of gravity equals 98. Okay, now either of these ways of indicating gravity are acceptable on a test or a quiz. Writing this is an acceptable way to indicate gravity, F sub W. I've also seen just plain W. Alright, usually I'll use one of these. Okay, now somebody is also pushing down on it. I'm going to draw this vector shorter because it's only 40 newtons. If somebody or something is adding a force to the situation, we usually call that a force applied. So F sub A is how we would indicate that. Okay, now what's F net? Still 0 newtons. The thing is still stationary, so all the forces have to cancel. Okay, that means the desk is going to have to work a little harder. So we're going to have to take the 98 plus the 40, and our normal force is going to be this time bigger than mg, bigger than the weight. Okay, so that's going to be F normal equals what? 138. Okay, yep. Okay, now that's a good question. The last unit we were all into negative signs and negative accelerations and all that. For these, we let the diagram tell the direction, and we don't often put the negative in. You'll kind of get used to that as we do a bunch of examples. Good question. Okay, next one. Someone is pulling up with 40 newtons of force on the same box. Okay, so gravity's still acting. The thing still weighs 98 newtons, even though someone's pulling up on it. So force of gravity, still 98. Okay, this time the applied force is up. Okay, and the question is the thing going to lift off the surface? No. Okay, the person's pulling up on the thing, but it's not actually leaving the surface. Okay, they're just kind of helping the desk out a little bit. So the desk doesn't have to push up as hard. The contact force goes down. Okay, what's it go down to? Okay, so normal force, I'm going to draw it a little bigger than the force applied. Force normal is equal to 58 newtons. And F net is still 0. Total force is still 0 newtons. These two forces cancel that force. So 40 plus 58 is 98, so everything is still canceled out. Okay? It's like me pulling up on this. Alright? F net's still 0. I'm just helping the desk out a little bit to counteract gravity.
Even though, like, then it's like a little bit, the box is like a little, not lighter, but lighter.
Yeah, to the desk, the box is lighter now. If the desk were a scale, in other words, the scale would read less, because scales actually don't read your weight. Scales read your what? Nope. A scale reads which of these forces? Nope. Nope. You can start guessing now because there's only 2 answers left. Nope. Nope. A scale reads your normal force.
That's what it said.
Well, you got to say it louder. Okay, if you are on a scale and someone lifts up on you a little bit, okay, the scale is going to read less. The scale reads how hard it pushes up on you, not how hard you push down, not how hard the earth is pulling down on you. Okay, so you can cheat a scale, in other words. If you want to seem heavier, okay, and you're standing on a scale, if you want to seem like you're a beast, okay, if I'm on a scale right now, I just do that. Look, I just gained 30 pounds. Right? Okay, if I want to seem lighter and I'm on a scale, I just push up on this desk a little bit. Instant weight loss program. Okay. All right, now a person pulls upward on the box with a force equal or greater to the box's weight. Okay, so now let's say the force applied is 100. Okay, and mg, force of gravity, is still 98. Is the thing going to lift? Yes. Okay, so now F net is equal to 2 newtons. It is unbalanced by 2 newtons. And when we have an F net that's not 0, we can go and maybe calculate an acceleration using what? Physics. Okay, N2L, Newton's second law. So we have F net equals ma, or acceleration equals F net over the mass. Okay, F net is 2. Mass 10, so that it would have a really small acceleration of 0.2 meters per second squared.
So would the desk be breaking or the box is breaking?
No, so someone is lifting it off the desk. Okay, so that's a good point. So what does normal force go down to? Normal force is now 0. Normal force is a lazy force. It only works as hard as it has to. Okay, so if we go back here, normal force is supporting the whole weight of the box. Here, where the person's pulling up on it, normal force is decreased. It's not working as hard because somebody's helping it out. Okay, here, normal force is not going to work at all, which is a good thing. What if normal force just decided to be an overachiever and work hard?
Then we have a different normal force.
What if normal force of this desk was like, I'm going to work harder than the weight of that thermos right now? It'd throw it off the desk. If the normal force of your seat was like an overachiever and is like, I'm going to work really hard right now. Okay, faith gets thrown right into the air. You're welcome.
Wait, would you get thrown or would you just slowly start like?
Okay, so that's normal force.